Hello everyone, this session I will be discussing some properties of determinants. You know, a determinant of order 2, how to expand, order 3 also, how to expand, that I have explained in previous 2 sessions. One on the concept of determinant, introduction, and the next one was on Cramer's rule. This session I will be discussing how to find the value of determinant, or even to prove the determinant to be 0, under what condition it is possible, that I am going to explain today. Before that, I just remind you the 3 by 3 determinant and its expansion. The determinant of order 3, A1, B1, C1, A2, B2, C2, A3, B3, C3. If you expand it, its value is A1 multiplied by B2, C3, B3, C2 minus B1. I am expanding in terms of first row, B1 A2 C3 minus C2 A3 plus C1 into A2 B3 minus B2 A3. This you all know, but imagine a very high value, I mean maybe integer, maybe in terms of variable, maybe big fraction, are taken as entries of the determinant. How to expand, how to find the value of determinant in that case, mainly I will be discussing with you. Before we start, let us see one very important characteristic property of determinant. In a determinant, if you have all the entries in a row or a column, this one says 0 and then A2, B2, C2, A3, B3, C3, if you expand in terms of first row or in terms of any row or any column, the value of this determinant 0. I did not include this part in a property, and this is true for columns also. If there is A1, A2, A3, 0, 0, 0, C1, C2, C3, if you expand by the above rule, value of this thing is also 0. This is quite obvious. If you expand, then it will be 0. But when you are solving a problem at any stage, if you get 0, 0, 0 in a row or in a column, the value of 3 by 3 determinant going to be equal to 0. Okay. Now let us do properties of determinant. The first property is the value of determinant remain unchanged if its rows and columns are interchanged. I mean, let A equal to A1, B1, C1, A2, B2, C2, A3, B3, C3, then det A is A1, B1, C1, we find determinant of square matrices only, B2, C2, A3, B3, C3. This will have the same value if you take transpose, change rows into columns, the value of determinant will be the same. B1, B2, B3, C1, C2, C3. I am not proving it, no need to prove. If you expand in terms of first row here, the value of determinant you know. Same value you will get if you expand in terms of any row, any column, but first column is quite obvious. So we can write in this property that determinant of A and determinant of A transpose, they have the same value. Sometimes it helps us to solve problems. That's why we'll remember this one as a property of determinant. What this property stands for? If any two rows of a determinant are interchanged, then sign of determinant changes. What does it mean? Any two rows of a determinant are interchanged. It may be in case of columns also. So I just explained, no proof is required. A1, B1, C1, A2, B2, C2, A3, B3, C3. This has same value as that of A2, B2, C2, A1, B1, C1, A3, B3, C3. But there will be change in its sign. The magnitude will remain the same, there will be just a negative sign before it. So if you do this interchanging of two rows once only, then there will be a minus sign. Somebody has done this step, interchanging this with this, then this with this. It means if we do exchange between these two rows, then there will be -1 into -1, value will be +1. What we did there? Interchanging first and second row. And what we have done here? Interchanging the second and third row. Another negative sign will come. Value will remain the same. Negative in compared to this determinant, not in compared to this. Here it will be A2, B2, C2, A1, B1, C1. This will take A3, B3, C3 because you are interchanging with the third row. So A3, B3, C3, A1, B1, C1. This is true for columns also. Suppose we have done the operation in columns, that is A1, A2, A3. This will have the same value as that of this determinant. B1, B2, B3. A negative sign will be there. If you interchange twice, then again there will be negative sign, it becomes plus over there. Okay. Now go for the third property. For this property, if two rows of a determinant are identical, it may be in case of columns also, all corresponding elements are same, then value of determinant is 0. It means if we have a determinant of this form, A1, B1, C1, A2, B2, C2, and third row as A1, B1, C1, value is going to be 0. Okay. Maybe like this also, in case of columns also, A1, A2, A3, B1, B2, B3, and here it is A1, A2, A3. These two columns are identical, value of determinant must be equal to 0. Okay. All these proofs you can do on your own just by expanding in terms of any row or any column. Next one is very important, the fourth property. If each row of a determinant is multiplied by a constant, then value gets multiplied by k. Okay. It means if you write k multiplied by this thing, A1, B1, C1, A2, B2, C2, A3, B3, C3, you multiply the elements of one row only or one column only by k. Then it's fine. I am doing it in case of columns. K1, K2, K3, B1, B2, B3, C1, C2, C3. Okay. You can multiply the second row elements also, then it is valid. So remember, you are going to multiply only one row or one column. what you did in case of matrices. If you multiply a matrix by scalar, then all the entries are multiplied by the same scalar. But in case of determinant, remember that only one row or one column has to be multiplied. This will be, say, KA2, KB2, KC2, A3, B3, C3. Now, can we get the original step back? Of course. In a determinant, if a row or column multiplied by a scalar, then that scalar can be taken out. So, this is one application. Now, suppose I am just passing the remarks on it, okay? Then it will be, say, A1, B1, C1. This is 10A1, 10A2, 10B2, 10C2 and A2, B2, C2. No, this you take the same manner, that is A3, B3, C3. So what do you observe? The second row elements are multiplied by 10, so bring it out. B1, C1, A2, B2, C2, A3, B3, C3. Clear? Now, one immediate application of it in a determinant, if you find that two rows are proportional, then also value will be 0. Why? I am going back to this property. See, they are identical. Now, if it happens, another remark with the help of property 4. If we have A1, B1, C1, A2, B2, C2, KA1, KB1, KC1, the third row, then also value will be 0. Why? Because you can take K common. Now these two rows become identical. So if elements of one row is a scalar multiple of the other row, I mean, if you have a determinant like this, suppose say 10, 12, 13, 14, 15, 16, and this one say 50, 60, 65. So these two elements are scalar multiple of this, value will definitely be 0. And when you are answering objective questions, you put simply the value equal to 0. Okay? Let us go for the next one. If some or all elements of a row or column of a determinant are expressed as sum of or more two terms, then determinant can be expressed as sum of two determinants. This time, let me make it very clear to you just by considering this. This is true for columns also. Suppose you have A1, B1, A2, B2, A3, B3, C1, D1, E1, F1, G1, H1. This determinant is sum of these two determinants. These two will remain the same. A1, C1, F1, A2, D1, G1, A3, E1, H1. These two rows will remain the same for next one also. Just we will be taking the second element in this sum, that is B1, B2, B3, C1, D1, E1, F1, G1, H1. Okay, this is true for columns also. Okay, so whatever whether it is given in row or column, it doesn't matter. You can expand it as the sum of two determinants. Question arises, if there was determinant in this form, A1 plus B1, say plus C1, A2, B2, C2, A3, B3, C3, and this is C1. I have taken already C's, so I am taking as L1, M1, N1, L2, M2, N2. In that case, in this case, it will be sum of three determinants, that is A1, L1, L2, A2, M1, M2, A3, N1, N2 plus B1, B2, B3. These two will remain the same. L1, M1, N1, L2, M2, N2. This plus C1, L1, L2, C2, M1, M2, C3, N1, N2. Clear? So sum of three determinants. Question arises, if it happens in case of two rows, then what to do? If you have a determinant, say of this form, A1 plus B1, I am doing it in terms of columns, so that you realize that for columns also it is valid. C1, D1, C2, D2, and this is say L1 plus M1, P1 plus Q1, R1 plus S1, and this part is STU. Then how many determinants you will get? You can express as sum of how many determinants. What I do here, I write C1, C2, C3, then L1 plus M1, P1 plus Q1, R1 plus S1, STU, and here B1, these will come here, B1, D1, D2, L1 plus M1, P1 plus Q1, R1 plus S1, STU. Then this is sum of two determinants, delta 1, delta 2. This is again sum of two determinants, delta 3, delta 4. So you will get 4 determinants over there. If we have elements added over there, then we will get 8 determinants. All these things are belonging to basic properties, basic characteristic properties of a determinant. Some parts will be done in the next session, where I will show you factor theorem is valid in case of determinant, the differentiation of determinant is possible, and few more properties. Okay, so let us complete the next property. This is also very useful one, very useful one. If to each element of a row or column of a determinant, equimultiples of corresponding elements of other row or column are added, there is a gap over there, this should not be, then value of the determinant remains the same. So what do you understand? Again, if something true for rows, it will be true for columns also. This is the most applicable property in case of evaluation of determinants. I am telling you what? This is say A1, B1, C1, A2, B2, C2, A3, B3, C3. Then suppose I am multiplying this column by K adding over there, another scalar adding over there, value of the determinant will remain the same. I mean A1, A2, A3, if you say that B1 plus K1, B2 plus K2, B3 plus K3, C1, C2, C3. I did it in one column only, then value will be the same. Clear? At the same time, if you say that can't I add this column also multiplying by another scalar M, of course you can do. This is C1 plus A1M, A2M, and this is A3M. Then also value will remain the same. It means in a row or column, if you multiply by scalar all the elements, and that multiplication should be done mentally. If you really do it, then it will be wrong. And then you add to the elements of another row, or in case of column, or columns, then value will remain the same. Okay? Now, if I have taken k equal to 1, m is also 1, then what you are going to do? For k1, m1, you are writing a1, a2, a3, b1 plus a1, b2 plus a2, and this is c1 plus a1. Okay? So elements of one column you can add to other two columns. Elements of one row also you can add to the elements of another row or rows. For k minus 1, m is also minus 1. Then what you do? You subtract. There may be a case k equal to 1, m equal to minus 1. I mean elements of one row you are adding to elements of another row and subtracting from elements of the third row, then value will remain the same. True for columns also. Okay? All these properties will find application in solving some problems. But before doing that, if I want to demonstrate one very important concept here by using these properties, then it will be good for you. I am stating this manner. Prove that this is like a theorem. Prove that the value of a skew symmetric determinant of odd order is always 0. Prove that the value of a skew symmetric determinant of odd order is always 0. We are not struggling with fifth order determinant at this moment. Although for ISI-CMI, you have to keep the concept in your mind. Let me prove this thing by using a 3 by 3 determinant. I am taking a 3 by 3 determinant here, which is skew symmetric. This is skew symmetric determinant of order 3. We are going to prove the value of this determinant always 0. I mean, when you are answering MCQ, you can always put this. Let delta equal to this thing. First, we take the transpose. You know, value will remain the same. So you write or delta equal to 0 minus B1 minus C1. This was your first property. Changing rows into column, value will remain the same. And this is 0 minus B1 C1, this one B1 0 D1, and this one C1 D1 0. Okay, clear? Check once more. 0 minus B1, B1 0 minus D1, and C1 D1 0. Now what we will do here? We take minus 1 common from first row. So taking minus 1 common from first row, second row and third row. What do you observe? This will imply delta equal to minus 1. From one row you can take common. This is not matrix, you are doing determinant. This is the property we have learned. Minus 1, this will be 0 b1 d1 minus b1 0 d1 minus c1 minus d1 0. See, we got the same determinant back. So delta going to be what? Product of these 3 minus 1 is minus. Therefore delta plus delta equal to 0. This implies delta equal to 0. We'll always use theorems or properties in our following examples frequently whenever required. Okay? Let us see next one. What is the value of this determinant? See, entries are too large. Sometimes definitely we suggest expansion direct instead of using property, but this one is ideal for using properties. Okay, this is the value of delta. Delta equal to, I am using this property here, subtracting elements of this column from here. There will be no change. The value of k going to be minus 1. And then in the next step only, I just show you this one. 1990, 1991, 1992. You subtract these elements from here. It will give you 1, 2, 3. But don't do this. I'll tell you to do it bit quicker. But let me show you this method first. You may be confused initially if I involve all the 3 columns. So what I'll do there, I'll be subtracting this from this. That is 1, 1, 1. What you did here? C2 dash equal to C3 dash, C3 minus C2. New third column is obtained by subtracting second column from old one. Clear? Now what we'll do here? Or delta equal to 1990, 1991, 1992 and subtract this from this. It will be 1, 1, 1. So what we did here? These two operations you could have done in the same step to get the value 0. Why 0? Because 2 columns are identical. Value definitely going to be equal to 0. Isn't it? Hope you have understood. The properties I have showed you, and that only we are. In this sum, I will be showing you the property I have used for previous one. But simultaneously, I will be doing it for 2 rows or 2 columns. What I am going to do? This you write row wise. Subtract this from this. R3 dash is R3 minus R2. And then subtract this one from this one. So this remains unchanged. 2 square, 3 square. Here it will be 2 square minus 1 square 3, 5, 7 and here 9 minus 4, 5, 7, 9. Okay. Now what to do? I have used R3 dash, R3 minus R2, then I have used R2 dash equal to R2 minus R1. So just do one thing. This is 1, 4, 9, 3, 5, 7, 2, 2, 2. What I did here again? R3 dash equal to R3 minus R2 I have used. So 5 minus 3 is 2, 7 minus 5 2, 9 minus 7 is also 2. Now whenever elements of one row or column are identical, then use this situation to simplify, to get it quickly. I will be subtracting this from this and this, because if I get more number of zeros in a row, if you get all zero, value is 0. But if you get all equal to the same constant, then you subtract one from the other. So what I will do here, 1, 3, 2 will remain the same. We will subtract this from this and this. That is 3, 2, 0 and 8, 4, 0. Clear? So what I did there, I have used C2 dash equal to C2 minus C1, C3 dash is also C3 minus C1. You could have asked me, why not C3 minus C2? Why not? Because I wanted to show you a simple problem, various different manner. You can do the steps simultaneously. Definitely what I did. At the same time, one column you can subtract from two remaining columns. See allowed. Now 2 zeros are there. Your expansion will be easier. There is no hard and fast rule for MCQ that you have to use property only. If you find easier method, you expand. Expand is easier instead of property, you just go for it. Okay, if you expand it, its value going to be, I am expanding in terms of third row. Why? Because 2 zeros are there. This 2 into the corresponding cofactor, that is 12 minus 16, 2 into minus 4. Answer is minus 8 over there. This is the answer. Okay. Two consecutive sums are taken based on similar property mainly, just to make you habituated. All the operations vary for. The value of the determinant is independent of what? Three variables are there, n, a and x. On what quantity it is not dependent, that we have to find. First you think, for such a sum, will you be stick to your opinion that I will be using determinant for, properties for all sums? No. Change the sum. If you find it is easier to expand, go for expansion. Here property will not help. See, this if we subtract non-zero term, this if we subtract from here non-zero term, this is cos c minus cos t, will make the thing very complicated. This is again if we apply. So don't go for property. I have taken this sum just to show you that sometimes it is better for you to expand directly. I am doing it in terms of first row for your better understanding. This into this minus this into this. Cos n plus 1x, sin n plus 2x, and this minus sin n plus 1x. Clear? With a square done. With minus a, what will you get? Cos nx sin n plus 2x minus sin nx cos, and then plus 1 into cos x sin n plus 1x sin n plus 2x cos, this is cos nx, and this is this into this minus this into this. So there it will be cos nx sin n plus 1x minus sin nx cos n plus 1x. So if you evaluate, this is like sin a cos b minus cos a sin b. So sin a minus b, this angle is a, n plus 2 into x is a, and this is b. So there will be n plus 2x minus n plus 1x. Clear? That minus sin of, again sin a cos b minus cos a sin b, nx plus 2x minus nx plus 1 into sin a cos b minus cos a sin b. A is this thing, this angle, and b is this angle. Nx plus x minus nx. So it is a square multiplied by sin x, a multiplied by sin x plus sin x. So the result is independent of n. No n is there, all are x over there. Sin x into a square minus a plus 1. Okay? So it is independent of n. Clear? Hope you have understood. What is the value of this determinant? A plus b, a plus 2b, a plus 2b, a plus b, a plus b, a plus 2b, a. See, if you add all the elements, then you can do. Elements of 2 rows can be added to third row, or elements of 2 columns can be added to, that using K property. You are doing the operation twice. If you add elements of these 2 rows, that means second and third row to first one, the delta going to be a plus 2b plus a plus b, a plus b, a plus 2b, a plus b, a. This one a plus 2b, a, that is a plus b. Okay. What I did there? R1 dash equal to R1 plus R2 plus R3. So now this is becoming 3a plus b, 3a plus b, 3a plus b. So a plus 2b, a plus b, now this whole thing you can take as common, 3 into a plus b. If you take 3 into a plus b common, then is coming 1, 1, 1, identical. If you get identical, what I have told, use that element of one row or one column to subtract from other rows or columns for better simplification. So this will be 3 into a plus b. I have taken 3 as common, 3 into a plus b as common. Now subtract this from this and this. 1, 0, 0. The operation you write C2 dash C2 minus C1, C3 minus C1. So this will be a plus 2b minus 2b. This you are subtracting. First column. So there will be again minus b, a plus b, this is b only, and this is minus b. Alright? Now we can expand it. The value going to be 3 into a plus b, 1 multiplied by 2b square plus b square. See, 9b square into a plus b. So the answer going to be this thing. Just by the use of property. With expansion, you never think to get the answer so quickly. It will take long time. You have to factorize, you have to multiply, you have to eliminate. Okay. How to start with this sum? Already in property I showed you it can be expanded, it can be expressed as sum of 8 determinants. But we will not go for that. Writing 8 determinants is very time consuming. So try with different manner. See, when you are adding elements from two rows to another one, the value is going to be twice A plus twice B plus twice C. Am I correct? So go for that. Delta equal to, you do it row wise or column wise, no problem. So this will be twice A plus B plus C, twice A plus B plus C, twice A plus B plus C. What I did there? I did C1 dash equal to C1, C2, C3. They are added. All are added. C plus A plus B, B plus C, is that clear? Now delta equal to, or delta equal to what? You take twice 2AB, A plus B plus C. If you take common, it will not give you anything. So better you keep it there. A plus B plus C, A plus B plus C, A plus B plus C. Okay? 2 we have taken out. Then there is C plus A plus B, A plus B, B plus C. Now, to get this one, look at the right hand side. No summation is there. So somehow we have to get independent terms. So what I plan to do, I will subtract this column from this and this. Okay, if you subtract, this will be minus B, minus A, minus C, and here minus C, minus B, minus A. So what you did there? C2 dashed, C2 minus C1, you have used this thing. Now I can get it quickly if I add elements of these two columns here and then take minus common. What I told? See, minus B minus C, if it is added, I will be getting A over there. Minus A minus B added, I will be getting C over there. I will be getting B over there. So do that. Use C1 dash equal to C1 plus C2 plus C3. This is A, B, C. Okay, then you take minus 1 common from each of the two columns. 2 minus 1 minus 1, A, B, C, B, A, C, C, B, A. This is the sum. Okay, we got the same thing over there. A, B, C, just a minute. This will be C only. It's my writing mistake. Then this will be C and A added, it will be B only. Now it's fine. A, C, B. See, the right hand side is matching over there. So 2 into minus 1 is what? 2 only. There will be 2 over there. Clear? What to do with this? X not equal to 1 and delta equal to 1x x square 1x, x square 1. Then delta equal to 0. for exactly 2 distinct complex numbers, for exactly 4 distinct complex numbers, for 2, for none of these, whatever. This will give you a polynomial. Let us try to get the polynomial here. Again, like previous one, if you add elements of one row or one column to, two rows or two columns to the third row or third column, then they are becoming identical. So looking at that, delta equal to, I am writing 1 plus x square plus x, this time with row. You can take row or column, it doesn't matter. X square x1, and this is x square 1x, x square 1. We have done r1 dash equal to r1, r2, r3. So this is common, you take it out. Then there is 1, 1, 1. This is a fun. 3 sums we got this manner, terms are identical. So I will be using that concept, subtract this from this and this. Because I want to get maximum number of zeros for better expansion. Keeping this one unchanged, 0, 0 here, 1 minus x square, 1 minus x. So what we have done there? C2 dash, C2 minus C1, C3 minus C1. Okay. Now delta going to be 1 plus x square. Then there will be 1 minus x square, x minus x square. I am not expanding. All the properties equally valid for 2 by 2 determinant also. If you can use, we will definitely go for it. Sorry. So this is a determinant only. This will give us 1 plus x square, and then you take 1 minus x common, because this is 1 plus x. This is x into 1 minus x, minus x, 1 minus x, 1 minus x. You take 1 minus x common from 2 columns. 1 plus x square, 1 minus x from first column, 1 minus x from second column. Then what is remaining over there? X, 1 plus x, 1. If we expand it, and this is 1 plus x square. So this is going to be 1 plus x square into 1 minus x whole square. This is nothing but 1 minus x cube whole square. So big one, we got the value of the determinant. What is that? The value of the determinant is 1 minus x cube whole square, and that is given 0. So is it given delta equal to 0. So this thing 0. It implies x cube equal to 1. Therefore 3 roots are 3 cube roots of unity, you know. X is 1 omega and omega square. Clear? So exactly 2 distinct complex numbers are there for this one. Clear? And only one value. I am not discussing any ISI-CMI sum today or IITJEE even, but for better concepts I will be discussing some problems so that you can start doing PYQs. Okay? So this time the determinant we have to prove, which one we don't know, correct? is always divisible by what? That we have to see. 100, 400, 200 or 300. We will be using properties only. But see, here the problem is, no problem is there. You just add. This is going to be a square, b square, c square plus 20. Here also. And this one also. This is b square and again b square. Okay. So we have used R1 dash equal to R1 plus R2 plus R3. Now take this thing common. Then what do you get? 1, 1, 1. Okay. Now you subtract this from this and this. What from what and what? C2 dash C2 minus C1. Do this. So you will be getting 1 b square c square 0 0 20 0 0 20. Expand in terms of first row, there will be 20 into 20 400. So this is always divisible by 400. Our question is here. Divisible by what? We have proved that it is divisible by 400. And this one, alpha, beta, gamma are the roots of this equation. Then the value of the determinant is what? This is cyclic one. Next session we will be solving many sums based on this property. Alpha, beta, gamma, alpha, gamma, alpha, beta coming in cyclic one. Value can be predicted, but I am not going to do. I will be using properties only here. That delta is what? Add again like previous one. Alpha plus beta plus gamma, beta plus gamma plus alpha, similar to all previous ones. Beta gamma alpha, gamma alpha beta. So what you did there? You have used R1 dash equal to R1, R2 and R3. So delta equal to take alpha plus beta plus gamma common 1, 1, 1. Beta, gamma, alpha, beta. Now subtract this column from this and this. 1, 0, 0. Beta, gamma. And beta minus gamma. Now expand it because 2 zeros we got. This is going to be gamma minus beta minus alpha minus beta, alpha minus gamma. So just open the bracket. Gamma beta minus gamma square minus beta square. Again gamma beta minus alpha square minus alpha gamma and then gamma beta. So one gamma beta getting cancelled from here and here. This is alpha plus beta plus gamma and then alpha beta beta gamma, gamma alpha minus beta square minus gamma square. So what you get finally? The delta going to be equal to alpha plus beta plus gamma, and this thing, oh, they have given alpha plus beta plus gamma. No, they have not given. We just write alpha plus beta plus gamma is 0 because no x square is there. Although alpha beta, beta gamma, gamma alpha exists, it is B and alpha beta gamma minus C, but this part going to be 0. So the value of determinant at this stage only you can say 0. I didn't check that. I am sorry. So the delta going to be equal to 0. Actually my aim is to show you that this is going to be a very great result, delta equal to minus alpha plus beta plus gamma, alpha square, beta square, gamma square, and minus alpha beta, beta gamma, gamma alpha. This is nothing but alpha cube, beta cube, gamma cube minus 3 alpha beta. Okay, this is factorization of this. Hope you have understood this session on properties of determinant. Coming with more challenging sessions for you, where I will be discussing factor theorem in determinant, cyclic determinant. Okay.